Let's wait a couple more minutes, though. Maybe.
Yeah, I mean, have I really just scared everyone off?
Everyone.
Yeah. I mean, usually Ergun at least has been here. Yeah.
Ergun has been.
Yeah.
And companies on Zoom.
Oh, okay. Big pardon?
I hope.
Ah, yes. It's always a little dangerous.
Message. Okay, I think we're more or less complete. I'm okay. So today, Walker is going to talk about limits and colimits in higher categories, and this is supposed to be I think this is the last talk of the 4 talks in the sequence. Okay, so please take it away.
So thanks once again, both for the introduction and for the opportunity to give these talks. Yeah, as you said, today we're going to be finishing up this sequence of talks on higher category theory and quasi-category theory. And today we're going to be talking about colimits. And once again, this is going to follow what's probably a fairly familiar trajectory in that we're going to make a definition, justify it, state some results, some with technical proofs, some with sketches of proofs, and some entirely without proof. But hopefully, again, we'll get a little sense of the landscape of how one thinks about and works with higher categorical colimits. And once again, we're going to follow the same basic pattern as before. So we want to define higher categorical colimits. So what we're going to do is first examine the category of cones over a functor f from, let's say, I to C of ordinary categories, 1 categories. We're going to duplicate the definition for simplicial sets, and then we're going to define a colimit to be an initial or terminal object in the appropriate infinity categorical sense. And then a lot of the first propositions that we're going to look into will basically be sanity checks. They'll be ways of convincing us that the definition that we've given is the right one. So let's start out for 1 categories. So we have some functor f from I to c, and let's denote by c over f the category of cones over f. So schematically, this will have objects that look as follows. Well, over here we can give some sort of schematic representation of the diagram f itself, some objects, some morphisms, and then a cone will be an object C and maps such that this commutes. And then if we have another object, or sorry, another cone, so again, something like that, we can define a morphism of cones between these two to be some map in C such that the appropriate structure maps commute with one another. Entirely the usual definition, but I've chosen the notation and the style of drawing to be somewhat suggestive. So both the notation and the way we've drawn this tell us, okay, well, a simplex in C over F, sorry, the nerve, is just going to be a map from delta n join the nerve of I to C that restricts to F on the nerve of I, right? So an object, when n is 0, is just you join one object additionally to the nerve of I, and you get this map into C. And a morphism is you join a one simplex to the nerve of I and have this map into C that restricts on the nerve of I to F. So what this tells us is that the nerve of C over F is the nerve of C over F, where this thing we defined previously, I think this was 2 talks ago, something like that, by specifying that an n simplex in, say, x over f is the same thing where, so now f from k to x, map of simplicial sets, is the same thing as a map that restricts to f on delta n join with k to x. So this tells us that we already have a ready-made category of cones, and we actually already showed that these sort of slices, if we start with a quasi-category and then slice it in this way, we still get a quasi-category. So we've already encountered, in some sense, our infinity categories of cones over a functor. But still, let's turn this into a definition. So let's let K be a simplicial set, C a quasi-category, and F from K to C a map. The quasi-category of cones over F is C over F, just this simplicial set, a limit of F is a terminal object in the category of cones. So this is literally word for word the definition that you would give one categorically, just expressed now in terms of this quasi-category of cones. Yeah? Yes, gave two definitions. In the first talk, we just said take the rigidification and require that all of the mapping spaces into it be contractible. In the second talk, remember we defined mapping spaces in terms of C over X to C, pullbacks of that. This is what we called map R, C, Y, X. And we showed that these are models for the mapping space. And this is a trivial fibration, a trivial confibration, if and only if these are contractible. So we have those two definitions, and I'll be leaning a little bit more heavily on the latter of those. Okay, so that's limits. And now we can say dualize the definition. And there are a couple of ways to do this. One is just to consider the opposite category, but the other we can just change over to under, C over F to C F over, the other slice that we defined, limit to colimit, and terminal to initial. So we have this definition, and the first thing that we want to do is convince ourselves that this isn't a crazy thing to define. And there are a couple of heuristic reasons that we should believe that this is sensible. The first is which, as we've already shown, since everything in the Joyal model structure is cofibrant, maps out of any object capture coherence in a meaningful way. And so a map like this, delta, or better, like this, from delta n star k to x, is already capturing some coherent information. And so this category of cones is a reasonable choice of a coherent category of cones, or a category of coherent cones. And similarly, our notion of terminal and initial is fundamentally the infinity categorical notion. It's about contractible spaces, not about singleton sets. And so this tells us a priori that we might trust this definition reasonably well. And so we're going to now go through a couple of sanity checks. The first one, I'm just going to state as a fact, because we haven't even developed the technology to state it rigorously, let alone prove it. So, let me first fix some notation. For X, a simplicial set, let's write X with a right pointing triangle to mean X joined with a zero simplex on the right-hand side, and X left pointing triangle to mean a zero simplex joined with X. So what this means is a colimit of F is going to be, or actually more general, limit of F is going to be a map from K with this leftward pointing triangle to C, because it's an object of this category of cones. And then our first sanity check is the following fact, which again, I'll be stating without proof. A I keep on writing colimit, a limit cone f from k to c induces a natural equivalence. And let's say for this zero simplex, I'll always just denote it by v. So the cone point will always be v. So this induces a natural equivalence, maps in C from B to f of v to maps in functors from K to C from, and I'll explain my notation in a moment, F restricted to K. Okay, so here, this is hopefully relatively reasonable. We have the mapping space in C from B to the cone point. So this is the thing that we think of as the colimit. And here we have maps in the functor quasi-category. So this is natural transformations. By this underline K, I mean the constant functor. And the reason that I don't use the notation delta that shows up in a fair number of places is because we already have quite a lot of deltas to be dealing with. So underline B sub K, this is the constant functor, K to C, which sends everything to B and to degenerate simplices on B. And then this F restricted to K is just we take our limit cone and we restrict to the functor whose colimit we're taking, or limit we're taking. I keep on doing that. Every single time I write colimit and I mean limit. So again, this goes well beyond our ability to even fully state, let alone check, because we haven't talked at all about higher categorical Ionata or what it really means for this to be natural. And we haven't really defined the functor involved here. We've defined these individual mapping spaces, but this would take some work. However, this is true, and I will make some use of it later. However, our second sanity check is something that we can check more immediately, and this is the following lemma. If f from K to C has a limit, the full simplicial subset of C over F on the limit cones is a contractible concomplex. So this is the infinity categorical version of the statement, thing is unique up to unique isomorphism. So we say a foo is unique up to unique isomorphism if the infinity category of foos is a contractible concomplex. There's really only essentially one way of getting from one thing to the next. Okay, so how do we prove this? Well, suffices to show that if C has a terminal object, the full simplicial subset of C on the terminal objects is a contractible concomplex. So we can consider a lifting problem to C to delta n, because if every such lifting problem has a solution, then of course C is a contractible concomplex. And let's restrict to n greater than or equal to 1. Because in the case where n is 0, so let's say this is G, and such that G of I is terminal in C for every I in N. So we can restrict to the case n greater than or equal to 1, because the case where n is 0 is just saying we have the empty set, and we want to lift that to a terminal object. But we're already assuming that there is a terminal object. So the case n equals 0 is completely trivial. And then we can do another one of these funny combinatorial tricks, which is that the boundary of delta n is isomorphic to, let's see, this will be boundary of delta n minus 1 joined with delta naught, coproduct over boundary of delta n minus 1 joined with the empty set, delta n minus 1 joined with the empty set. Heuristically, you can think of this as saying we have, for instance, the 3 simplex is constructed out of the boundary of a 2 simplex joined to a point, and then we glue on the remaining face, which is that 2 simplex joined with nothing. And the corresponding decomposition of delta n is just delta n minus 1 joined with delta naught. So this means we can apply what is quickly getting to be our favorite trick, namely pass to the adjoint lifting problem. So the adjoint lifting problem is of the form boundary delta n minus 1 to C over G of n delta n minus 1 to C. We want to know if that lifts. But this allows us to use our characterization of terminal objects that I mentioned in response to Radi's question. Namely, since, let's just call this pi, since Gn is terminal, by hypothesis, pi is a trivial configuration. And so, this lift exists. And we're done. So, this sanity check tells us that we really do have the desired uniqueness properties, right? The point, in some sense, of limits and colimits is to construct things in a sufficiently universal way that you're really uniquely specifying them. And that's precisely what this is saying. If we have an object equipped with a limit cone, then what we get is a unique morphism to any other cone up to contractible choice. And again, because we're working in higher categories, that up to contractible choice is completely inevitable. That's the only notion of uniqueness that makes sense higher categorically. Okay.
The reason I asked about
Mm-hmm.
the definition of many places they start boundary filling property.
Sure.
And so then this fact is sort of by definition.
Right.
But you have started with the mapping spaces
Yes.
and then
Yeah, so we started with the mapping spaces definition. We showed that it implies that this is a trivial confibration. And then from that, you get this uniqueness. And I would say that's sort of the way the reasoning goes one categorically. And so to me, it makes sense to present things higher categorically as well, right? When you're defining a terminal object one categorically, you say it's a thing such that mapping spaces into it are all singletons. And then you derive some properties of it. But yes, so that is sort of the path that we took to get there. Yeah. Okay, so the final sanity check is again going to be something that I'm going to state without proof, but is quite important, and it's the following theorem. So let I and C be con-enriched categories. So simplicially enriched categories whose mapping spaces are all con-complexes. And F from I to C, a con-enriched functor. A cone from X to F of I over F induces a cone eta bar from the coherent nerve of from coherent nerve of I to coherent nerve of C. Moreover, the following are equivalent. First, the set of the eta I is a homotopy limit cone. And second, eta bar is a limit cone, where we take limit cone in the infinity categorical sense. So what this is saying is basically, in the most general setting, you can reasonably define homotopy colimits, or not the most. In one of the most general settings, you can define homotopy colimits in. Homotopy colimits are the same thing as infinity categorical colimits. And so from this, we can deduce, for instance, that a lot of well-studied infinity categories have all limits and colimits. So for instance, we can deduce that the infinity category of spaces, which we defined to be the homotopy coherent nerve of the simplicially enriched category of con-complexes, has all limits and colimits, because it has all limits and colimits in the homotopy sense. Yeah. Yeah. We have not defined that. Loosely speaking, you define this using the universal property that colimits get sent by the mapping space functor to limits. And so you have a well-defined notion of a homotopy limit of spaces, or a homotopy limit of simplicial sets. And then you require the universal property that map colim I f blank is naturally equivalent to lim I op map f blank.
We have lim also on the left-hand side. Are we talking about limits or colimits?
Both, sorry. If you want that. It's just the same thing applied to the opposite category. So the slogan here is Uneta commutes with limits. And so you require, or you define a homotopy limits to be a thing that satisfies this universal property, where this is now holim and holim.
Yeah, this makes sense. So the example there,
Mm.
saying the homotopy coherent nerve,
Mm.
so that's supposed to be
The infinity category of spaces. Right? The objects are concomplexes, the zero simplices, if you like, and the mapping spaces are just the simplicial mapping spaces between concomplexes.
right. I'm a little confused about what is happening in which part. So there's a simplicial category and the quasi-category.
No, so these are just con-enriched categories.
Okay.
What this is saying is the homotopy limit of a functor into a con-enriched category is the same thing as an infinity categorical limit of the functor, the corresponding functor, into its homotopy coherent nerve.
The homotopy coherent are little landed.
This is a quasi-category.
Yeah, okay, so that's what I was asking.
Yeah.
Okay, so now I think
Okay.
this is a quasi-category, and we have limits and colimits.
Yeah.
On the other side, we have colimits and
Yeah.
everything is coming from.
I'm also about to give an explicit construction of the limits and colimits, but yes, because there are homotopy limits and colimits on this side, on the simplically enriched side, you get infinity categorical limits on the quasi-categorical side.
Thank you. Basically, coherent nerve takes traditional notion of colimits.
Yeah.
Quasi-categorical.
Exactly, of limit or colimit. Yes. And it's also worth noting that there's a large class of con-enriched categories that have all homotopy limits and homotopy colimits, because if you have a sufficiently nice simplicial model structure, then you get them for free. And so, for instance, that's one of the ways that we can know that this has all homotopy limits and homotopy colimits. However, one can also compute more directly what these homotopy limits and homotopy colimits are. And this is a collection of theorems that we've actually already seen one example of earlier on. So there was a talk at the beginning of the semester, I don't remember precisely when, in which Thomason's theorem was presented for computing certain homotopy colimits in terms of Grothendieck constructions. And so the idea here is that if we have some f, well, okay, first let me say there are two Grothendieck constructions. Last time I got a little pressed for time, and so didn't get to mention the other variants, but so given, say, f from we have, on the one hand, the one that we talked about last time, the unstraightening, now this would be over k op of f going to k op, and this is a right fibration. And this is sometimes called the contravariant. Grothendieck construction. But we also have unco k of f that just goes to k, which is a left fibration and is called the covariant Grothendieck construction. So if you remember from the last talk, when we were constructing the adjoint, the straightening functor, we used a join, and we adjoined this point on one side. Basically, the difference between the two constructions is which side you adjoin the point on. Reverses the direction of your arrows, so to speak, and so you get one functoriality or the other. So these are the two Grothendieck constructions, and the claim is basically that, in a sense, one of these computes colimits, and one computes limits. So, given f from k to spaces, remember, spaces is just the homotopy coherent nerve of con, which means that this is equivalently, by adjunction, a map from the rigidification of k to simplicial sets that takes values in the con complexes. So given this, the claim is that the limit of f is the space of sections of the contravariant Grothendieck construction, and the colimit is just the covariant Grothendieck construction itself. Now, it's worth pointing out there's a little bit of a subtlety here. When I say the colimit is this is not actually a con complex. In general, this is going to be a quasi-category, but not a con complex. And so you have to confibrantly replace it. So what this is really saying is that the realization of this, or the confibrant replacement of this is, but this has the correct homotopy type. So we can turn these into more formal statements. So theorem. Let f from k to s be a functor and f, whoops, a cone. The map, let's see, from the mapping space in simplicial sets over K op from K cone op to the unstraightening over K cone op of F to mapping space in this same category the cone point to un K cone op F is a weak homotopy equivalence. You can actually say something stronger. It's a trivial fibration, but for our purposes, that's all one needs. So this thing is just maps into the fiber over the cone point. But the fiber over the cone point is identified with f of v. Moreover, f is a, whoops, this should be, is a limit cone if and only if, and I'm running out of space, the map from map set delta over this thing. So again, this guy right here. To map set delta over k op on k op f is a weak homotopy equivalence. Okay, so here you take this entire functor, this cone as a functor, and you straighten the whole thing, or unstraighten the whole thing. Here, you're just unstraightening f itself, the restriction to your original functor. So this is the thing that we claimed was the limit. This is just sections of the right fibration on kf to k. It's equivalent to this thing if this is a colimit, but precisely when this is if this is a limit, but precisely when this is a limit. And then this is always an equivalence.
So which part is supposed to be computed?
This is computed by this, right? This is the space of sections. This is the limit cone under these assumptions. Now, why do I write it out in this much detail? Because this gives hopefully a little bit of insight into how one can establish the naturality of something like this in a very computational way. So like, this is actually a natural weak equivalence in the sense that if you have a transformation of functors and cones, you get an induced map on Grothendieck constructions, and you get Or, for instance, if you have a map from, say, x to k, you get induced maps on each of these that can commute with these maps. And so this tells you how the naturality of the Grothendieck construction can be, or sorry, the naturality of the limit can be established in a very computational way. Yeah, you have an explicit zigzag. And the statement for colimits is similar. I'm not going to write it in its entirety because, as you can see, this is all a little long. But again, let's have f from k to s a functor. And now a cone. So here in the middle, we're still going to have un over k, but now co of f. So we unstraighten the cone. On the one hand, we can include the unstraightening just over v of f restricted to the cone point. And this is always going to be a weak equivalence. And again, because this is just the Grothendieck construction over a terminal category, this is always going to be identified with just f of v, the value of f on the cone point. And then there's a map on k f. Sorry, all of these are covariant. And the statement for colimits says, this is a colimit if and only if this is an equivalence. So same style of statement, arrows point the other direction, not entirely surprisingly. But again, all this is doing is it's identifying the cone point with the unstraightening, with the Grothendieck construction, precisely when this is a limit cone, or sorry, a colimit cone. This is the colimit. Colimit is just this. Limit is a space of sections. Yeah. Like the classical version of Thomason's theorem that we saw a month or two ago is more of the second form. It just says the homotopy colimit is the Grothendieck construction.
Oh, yes, okay. Oh, okay.
Yeah. And now I should say, again, I had intended to discuss the Grothendieck construction for more general functors into infinity categories last time, but didn't quite get around to it. But let me just say that there is a version here where now this is the space of Cartesian sections. So sections that send every morphism to a Cartesian morphism. And this is a localization. So if we instead consider functors into the infinity category of infinity categories, we still have variants of Thomason's theorem that compute limits and colimits in cat infinity in terms of Grothendieck constructions. They're now a little bit more involved, but again, not a very different form. One thing to actually point out is that this statement, I told you this is not fibrant as a concomplex, it is a quasi-category, and so in some sense, what we're saying when we're saying the confibrant replacement of this is we're saying localize infinity categorically at all morphisms. Confibrant replacement is just forcing everything to become an equivalence. Further questions? Mhm. Mhm.
And one can follow what you explained there. Do themselves.
Sure, yes. So the one can also use Groton deconstructions to like classical one-categorical Groton deconstructions to compute homotopy colimits of groupoids or of one-categories in much the same way, or homotopy limits. There, the localizations are one-categorical localizations. These spaces of sections are categories of sections. But the statements hold mutatis mutandis. And there you're right, it is easier to work them out, although still quite time-consuming. Other questions or comments?
Okay, so that infinity case there,
Yes, so this infinity category of spaces is a subcategory of cat infinity.
okay, so when you say localization, what is the model structure?
So this is, no, not a localization of a model category. Sorry, a localization as an infinity category. So taking this quasi-category and forcing certain things to become equivalences.
Oh, that's what you meant.
Yeah, yeah. So roughly speaking, the universal property of localization is that, let's say we have C, a one category, and W, subset of C, then functors from C, W inverse to any D should be the same thing as functors from C to D, which send all of the morphisms in W to equivalences. And you can define basically exactly the same thing higher categorically. You can say the infinity categorical localization of C at some collection of morphisms is the simplicial set, the quasi-category that satisfies this property.
What is W in that case? When you localize it?
You localize it at the set of all Cartesian morphisms. So in the case where it factors through spaces and this becomes a right vibration, every morphism is Cartesian, and so you localize at everything, and you get precisely the statement that we just gave. The colimit is just the localization at everything, is that space, confibrant replacement. In the case where it actually takes values in quasi-categories, you get something more complicated. Other questions? Let's see how I'm doing on time. Okay, not bad. So the last thing that I want to talk about today is cofinality. And this is basically the way you change your indexing category without changing the colimit. And so again, it's a computational technique. It says that if you have a map of a functor between your indexing categories for colimits, you get an equivalence between their colimits or limits. Now, I should also say, I am following the terminology in higher topos theory, so I'm calling this cofinality. However, the terminology surrounding cofinality, this notion that I'm about to talk about, is, for want of a better word, a clusterfuck. The same notion is sometimes called, so what I will call a cofinal functor is sometimes called a final functor, is sometimes called an op-final functor. I think that there's at least one source that calls it a co-initial functor. And so the terminology surrounding this is just useless, and do not rely on my choice of terminology or anyone's choice of terminology here. So definition. A functor f from C to D of quasi-categories is called cofinal if for any quasi-category E, a map G from D triangle to E is a colimit cone if and only if G of F is a colimit cone. So what this is saying is that it doesn't really matter if we're computing colimits indexed by D or colimits indexed by C. They're the same thing. There's this canonical way of identifying them. And my hope is to give a sketch of the argument as to how you characterize these cofinal functors between quasi-categories. However, it really is just going to be a sketch. There are a number of different proofs in the literature. All of them require more technical input than we currently have. I'm going to give a sketch that looks like I'm arguing sort of universally in terms of universal properties, that is. And I'm going to point out where I'm making use of technical lemmas. Yes. Where you just are the identity on that cone point. So the key proposition, and the one where I'm going to give at least some proof, although very sketchy proof, is the following. A functor f from C to D is cofinal if and only if for every right vibration P from E to D, the map maps over D from D to E to maps over D from C to E is a homotopy equivalence. So the sketch that I'm going to give is basically a chain of natural equivalences between mapping spaces. I will try to point out where I use things unjustifiedly. Know that all of them can be justified, and one can turn what I'm about to present into a more rigorous proof, but it is not in the form that you'll be seeing it. So, okay, let's let F be cofinal, so the first direction of the implication. And E to D, a right vibration. Let's choose G from D op to the infinity category of spaces such that un dg is equivalent to E. Right? By the Groton deconstruction, there's an equivalence between right fibrations and functors into spaces. And so we're going to choose one to classify it. And now let G bar from D op to S be a diagram in S extending G. Okay, so already there's something a little wonky going on. We've taken D op, and we're taking a limit, even though our statement is about colimits. But because we have this D op, this means that F op from C op to D op has to have this property, but now with respect to limits, right? The op reverses limits and colimits. So since F is cofinal, G bar of F op is also a limit cone. So now we can write maps over D from D to E is equivalent to maps in functors from D op to S from the constant functor on the terminal object D, because this is right fibration with all fibers trivial, D to D, the identity, to G. This is just by the Groton deconstruction. And then by the universal property of the colimit, this is maps from just the terminal object to G bar of V. And this is equal to maps from, maps in spaces, G bar F of V. So this is universal property of the colimit. And then by cofinality, we know that G of F op is also a limit cone. Sorry, this should be an F op. And so we get that this is maps in functors from C op to S of the constant functor on C, G composed with F op, which is, by the Groton deconstruction, maps over C from C. And now I'm going to be using, well, I'll write it down and then explain. Okay. So we take the first mapping space that we're interested in, we turn it into a space of natural transformations between functors by passing through the Groton deconstruction. We then apply the universal property of the limit, and then cofinality and the universal property of the limit. And then what we get is that this should be equivalent to the unstraightening, the maps between the unstraightenings of these two. Well, we can identify the unstraightening of this constant functor with just the identity from C to C. And we can identify un-G of F with the pullback C, oops, this was C crossover D on G. This is a functoriality result for the Groton deconstruction that we didn't have time to get to, but hopefully it's at least believable, as it is fairly apparently true in the one categorical case. So a couple of things that make this not entirely rigorous at this stage. For one thing, one should really be tracing through this sequence of equivalences and making sure that what one gets really is the map that I'm asserting is an equivalence. The other is this universal property of the limit I have stated, but haven't come anywhere close to proving. I haven't even constructed the map that I claim is an equivalence. So this is an argument that can be made rigorous, but at this point, we have a number of gaps in it. Let me see how much time I have. Do I want to write down the other direction? Probably not. So the other direction is a similar chain of mapping spaces with a couple more not yet justified results. But let me instead try to dwell on a little bit what this means. So the upshot. Well, what is this really saying? This is saying we have a functor between quasi-categories, and it's cofinal if and only if, whenever we test it against a right fibration, we get an equivalence of mapping spaces. But the upshot here is that if you test against every fibrant object and get an equivalence of mapping spaces, that means the original map has to be an equivalence in your model structure. So F from C to D is cofinal if and only if the following diagram, F identity, is an equivalence in the model structure for right fibrations. Because we've tested against every, inducing an equivalence on mapping spaces when you test against every fibrant object is the same thing as being an equivalence. So, thus, if FDC is a fibrant replacement of C in set delta over D, then, I should say F from C to D, then F is cofinal if and only if the fibers of FDC over D are contractible. So why is this? Well, the fibers of the identity map are contractible. And we proved last time that a map between right fibrations is an equivalence if and only if the induced maps on fibers are weak homotopy equivalences. So this is more or less as far as we can go for the time being, but there is one technical lemma, or let's say technical proposition, which allows us to retrieve a fairly classical result on homotopy cofinality from this statement. This technical proposition is that there is, or let's say, the fibrant replacement FDC has fibers equivalent to fiber, let's say fiber over D in D equivalent to C over D, which is just the pullback over D. So this is the slice of the functor f. And from this, we can retrieve the criterion that we're more used to for homotopy cofinality, which is namely that these slices of the functor f are all contractible. So this is one way that that can be proven, is by explicitly computing a fibrant replacement of this map, this functor, in the model structure for simplicial sets over D. I should say, when I say explicitly computing, it's more like you can really write down explicitly a replacement for that as a Cartesian fibration. And then you can show that forcing it to be a right fibration amounts to just localizing at the fibers. So there's a model for the Cartesian fibration that really does have these fibers on the nose. And then to get a right fibration out of that, you just need to localize the fibers. Okay, that's more or less all I wanted to say today. Are there any questions? I realize that today was sort of a big technical blowout, but I wanted to get through a little bit more since this is the last talk that I'll be giving on the subject. Mm-hmm.
So in the statement of the proposition,
Yeah. Yeah.
for a right vibration.
Mm-hmm. So this is sections of E,
Yeah.
if you want. And this is maps from F to E that live over D.
There's a sense in which
Mm-hmm.
right, at least not trivial technically.
Mm-hmm. Sure.
But we think in terms of the perpendicular. I don't know what that is.
What is saying? Here, this is perhaps something that we can discuss afterwards.
Yeah, okay.
Yeah.
That's a better idea. Thank you very much.
Any questions on Zoom or here? Okay, so thank you, Walker, for this sequence of talks. I think this was the final one.
Yes.
Okay, yeah, thanks.
Thanks very much.